Hello everyone, today we're going to go over the algebraic theory of spin and the famous Pauli spin matrices. Now, if you guys can remember, from the first video in this playlist on spin, we discovered spin by doing the Stern-Gerlach experiment. Basically, we have two weirdly shaped magnets. We shoot a particle through those magnets, and it gets either deflected up or down. If it gets deflected up, we say that it's in the spin up state. Down, then it's in the spin down state. And we went over how to calculate the probability that it gets in the spin up state or in the spin down state by analyzing the spinor prior to the measurement. Now in this video, we are going to go over the algebraic theory of all of this, kind of like show the formalism of spin itself. So it's going to be really cool. So let's start. So what we do is we define commutation relations of spin operators. So we define commutation between Sx and the Sy operator as I h bar Sc. Commutator of Sy Sz is going to be I h bar Sx. And the commutator of Sz and Sx is going to be I h bar Sy. Now this may seem peculiar to you guys. So why are we doing this and what are we doing? Well, what we are doing is we are just defining commutation relations between these operators, and we're going to go over what these operators really mean later in this video. And you guys also might be wondering, why are these the solutions to these commutators? We haven't even written what the operators were in the first place. Well, we're kind of defining the commutation relation of these operators to be this, but we can actually find out why they're this when we consider rotational symmetries, and that kind of ties into Noether's theorem. And if you guys want to learn more about that, I recommend reading chapter 6, I believe, of Griffith's Quantum Mechanics. In the in the page about spin, it talks about how we actually get this. But for now, take this as a postulate for these commutation relations. So, all right. So also, we have some operator. We call this operator S squared, and it acts on some state Sm. And it gives us h bar squared s times s plus 1, same state Sm. So what we have here is we just have some operator that they call S squared. And this operator is acting on some state Sm, where S is called spin, and M is called the angular momentum quantum number. And it returns the same state, but scaled by some constant. And this is, of course, going to be an eigenvalue. Again, we haven't talked about what this S squared or Sx or Sy or Sz means. All we're doing is we're kind of like defining how they interact, and from there we can kind of talk about the physical significance of each of these operators. Now, something interesting here is that this state, we have S and we have M. So what does this state really mean? Well, M is the angular momentum quantum number, and it's of course associated with angular momentum. But S is said to be the spin quantum number. Now, spin is a bit harder to describe in angular momentum. And I'm not sure if I can really explain it well in this video. But spin, people say it's intrinsic angular momentum. But how I like to think about it is kind of making an analogy to ordinary quantum mechanics. So say I have like some wave function. Okay, I have some wave function, psi n of x. This is just some like normal wave function in quantum mechanics. Now n, I can take on values like 1, 2, 3, 4, and so on. And it gives us psi 1 of x, psi 2 of x, psi 3 of x, and so on. So psi of x is the wave function. In taking the modulus squared of this, it can give us probability densities. But n is not really psi of x. N just tells us kind of the possible values for psi of x. you have psi 1x, psi 2x, psi 3x, we can have psi 1/2 of x. So n is kind of like a, you can think of n like a kind of a judge that kind of like allows psi x to take on certain values. It quantizes psi of x. That's how I think of spin in this case. Spin is just like, it's just a number, like psi n of x. It's not this n here. That's not spin. It's just an analogy. But spin is like, it's like a number that kind of tells us the possible spin states we can have, sort of. And I'm gonna go into that about like right now. So here we have some operator acts on the spin state, gives us the eigenvalue times the spin state. Good. All right. Now, what we can do here is you can take another operator. We call this s plus minus, and it's just the square root of this operator, kind of. So it's the square root of h bar squared s times s plus 1 sm. All right. Now, the square root of h bar squared is just h bar. So you can kind of move that to the front of it. So you have h bar times the square root of s times s plus 1 times s, I believe, wait, just check if I'm doing it correctly. Actually, I think there should be an extra term here. There should be a minus m times m plus or minus 1 term here, then times s m, and this is what we call the s plus or minus operator, and it comes from this plus or minus m. And from this operator, we get possible values for s. S can take on 0, 1/2, 1, 1 and 1/2, 2, 2 and 1/2, and so on. So s can pretty much take on n over 2, where n is just some integer. So basically what we're saying here is that s is constrained to these values, sort of like how the n here is constrained to just 1, 2, 3, 4, 5, and so on. S can take on values 0, 1/2, 1, 1/2, 2, 2/2, and so on. Now m is that depends on s. And so what do I mean by this? Well, let me just make a new page here. So s can take on values. Sorry, I actually made a slight mistake. S can also be 0, by the way. So it can be 0, 1/2, 1, 3/2, and like so on. But m can take on values of minus s plus 1, all the way to s minus 1 to s. Okay, and m is the angular momentum quantum number, and s is the spin quantum number. All right. So we see that m is kind of constrained by what s is. For example, say s is 1/2. M can take on values of minus 1/2, then minus 1/2 plus 1, which is just 1/2. And since we've reached s, we can't have any more values of m. Say s is 0. Well, then m can only be 0, right? Say s is 1. Well, then m can be minus 1. Then minus 1 plus 1, which is 0. 0 plus 1 is 1. So m is constrained on s. All right. And then s is, of course, the spin of our system. Now, for spin 1/2 particles, s is said to be 1/2, right? Because that's what it means. Spin 1/2, s is 1/2. And this means that our values for m is minus 1/2 and 1/2. Now, in this video, and in this entire series, we are going to study spin 1/2 particles. So spin 1/2 particles, the key takeaway is that the angular momentum number can be minus 1/2 or 1/2. Now, I'm just going to say this up front. I apologize if what I said made no sense. I can't really explain this really well. Like, for one, because I don't understand it 100%, so I can't give a gold explanation. But I'm trying to explain it the best I can. So basically, the spin is like, the spin kind of tells us the spinors that are permitted in a way. So if spin 1/2, well then m can be minus 1/2, 1/2. So it kind of tells us what values of m we can get. That's how I like to think of spin. I'm sure there's like some better way of thinking about it, but that's just the best way, you know? There's also the picture of a particle that's spinning, which isn't actually correct. It's just an analogy. That's one way to think of spin. But yeah, this is how I think of it. Okay, enough blustering. Let's move on. So we say that spin 1/2 particles. Again, remember that the general state can be written as S M, and it's cats over here. So for spin 1/2, so for spin 1/2 particles, you plug in 1/2 for S. So we can have 1/2 and then 1/2. So here's S and here's M. Or we can have 1/2 and minus 1/2. This isn't 1/2 like subtracted by 1/2. It's just 1/2 for S minus 1/2 for M. Okay, and now this is kind of where it all comes together. We call this spin up, and we call this spin down. So if you guys were wondering, well, what does SM mean? Well, SM is pretty much just like the spin state. It tells us spin up, it tells us spin down. Taking a supervision of these can give us general spinors. So what we call spin up, well, it's pretty much the other way around. If a particle is in spin up, this means that its angular momentum number was 1/2, and the spin number was 1/2. If this particle is in the spin down state, it means that its angular momentum number was minus 1/2, and the spin number was of course 1/2, since we're studying 1/2 particles. So let's kind of go back to the String-Grog experiment. Have a particle, put it through this thing, this magnet that's shaped weirdly. The particle can go up, spin up, particle can go down, it's spin down. Well, now we kind of gain an extra understanding as to what spin up really means. So if it's spin up, it just tells us, so again, the particles that we are dealing with, they're spin 1/2. So if it goes up, it kind of tells us that the angular momentum number was 1/2. Spin down, it tells us the angular momentum number was minus 1/2. This might make us say, okay, well, why do we care about spin up and spin down? Why can't we just replace spin up with just m equals 1/2 and replace spin down with m equals minus 1/2? Well, we can't say that because m is actually, again, constrained by s. If we choose different values of s, well, then m can be different values corresponding to different physical situations. But for the spin 1/2, things are pretty simple. Since the spin up state corresponds to just one value of m, spin down state corresponds to just another value of m. Sorry, ignore the other people talking. Right, sorry about that. All right. So now we can finally talk about what those operators that we mentioned at the start actually are equal to. So let's start out with the s squared operator. If you can remember from earlier, s squared acts on oh, actually let me just write it down again. So s squared acts on sm, gives us h bar squared s times s plus 1 sm. And again, we are studying spin 1/2 particles, which means that s is 1/2, right? So this means that s squared of 1/2 m equals h bar squared times 1/2 times 1/2 plus 1 times 1/2 m. So now you have h bar squared over 2 times 1/2 plus 1 times 1/2 m. And now this gives us 3 over 4 h bar squared. 3 over 4 h bar squared times 1/2 m, right? You just distribute this h bar squared into here. Now if m equals 1, well then s squared, let me just move this up a tad bit. If m equals 1, then this means that s squared acting on 1 half is 3 over 4 h bar squared times 1 half. If m equals, wait a second, no, not m equals 1, if m equals 1 half. And if m equals minus 1 half, well then this spin operator, squared, acts on 1 half minus 1 half, gives us 3 over 4 h bar squared times 1 half minus 1 half. Remember this 1 half, that's just spin up, right? And this is just spin down. So we can kind of simplify this a lot and say that s squared will act on spin up. It's going to give us 3 over 4 h bar squared spin up. And then as s squared will act on spin down, it'll give us 3 over 4 h bar squared spin down. Alright, and then these are our eigenvalues. And from this we can kind of construct our matrix for what s is going to be. Because s is an operator, so of course s is going to be a matrix. And since these spin states are 1 by 2 matrices, s is going to be a 2 by 2 matrix. So let's just write s squared. So let's write s squared as a matrix A, B, C, D. It acts on 1, 0, the spin up state, and it gives us 3 over 4 h bar squared spin up. If you guys are confused about why spin up is 1, 0, I recommend watching my first video on spinors. So act on this state gives us 3 over 4 h bar squared times spin up state. Alright. Then analogously, it's going to act on the spin down state and give us 3 over 4 h bar squared times 0, 1. So from this, we can actually find out what s squared, the components are going to be. So let's start out with the spin up state. So let's just rewrite this. A, B, C, D times 1, 0 is 3 over 4 h bar squared times 1, 0. So let's actually multiply these together. This gives us, well, a times 1 is a, b times 0 is 0, c times 1 is c, and then d times 0 is 0. So ac equals 3 over 4 h bar squared 1, 0. So that's 3 over 4 h bar squared 0, implying that a equals 3 over 4 h bar squared and c equals 0. Alright. So what about the spin down state? Well, we have A, B, C, D acts on 0, 1, gives us 3 over 4 h bar squared times 0, 1. Alright, same thing here. Doing this matrix multiplication, we get BD equals 0, 3 over 4 h bar squared, implying that B equals 0, D equals 3 over 4 h bar squared. So we have A, B, C, D is going to be equal to 3 over 4 h bar squared. C is 0. And then 0, D is 3 over h bar squared. And we've just found out what the s squared operator is going to be. So it's kind of like, so what we're doing is that we're kind of tying loose ends from the start. Before I was being pretty abstract. Well, you get this operator act on this, blah 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 blah. And because might be wondering, well, what is the operator? Well, what we did at the start was we used to find how some operator acts on other things, and from there deduced what the operator ought to be for those interactions to actually make sense. All right. So that's what s squared is. And doing something similar, we can actually find what sz, sy, and sx is. X plus and s minus. I'm not going to go through each of these cases because this video will be an actually like 10 minutes long. Try to keep my videos as short as possible while not compromising information that is non-trivial. So you guys can kind of work through what these would have to be yourself. I just did an example for s squared. But doing something similar, we actually get that SZ should be H bar over 2 times 1, 0, 0 minus 1. Alright. And if we can remember, what was the operation of SZ? Trying to find what SZ was. Like, here's SZ, but what operation do we use? Can't remember, but here's SZ. I'll try to find it at the end of the video, but here's SZ. It's going to be this. S plus is going to be H bar times 0, 1, 0, 0. And S minus is going to be H bar times 0, 0, 1, 0. Alright. And now we use the property that S plus minus is going to be Sx plus or minus ISy, which means that Sx is going to be H bar over 2 times 0, 1, 1, 0. Sy is going to be H bar over 2, 0, minus 1, 1, 0. And Sc is going to be H bar over 2 times 1, 0, 0, minus 1. And by the way, did not memorize this. I have a sheet right next to me, because no one remembers all of these matrices here, except like Dirac or Pauli. So what we can do now is we can kind of take some kind of like abstractify this a bit, make this a bit more general. Some general spinner, not spinner, some general spin operator is going to be H bar over 2 times times this sigma over here, and where sigma x is defined as 0, 1, 1, 0, sigma y is defined as 0, minus 1, 1, 0, and sigma z is defined as 1, 0, 0, minus 1. Alright. Oops, also forgot to mention here, we had this this h bar squared term here. We can actually factor that out. 3 over 4 h bar squared 1, 0, 0, 1 versus the identity matrix, by the way. But let's go back here, and these matrices are called the Pauli spin matrices. Alright, so this is the plus matrix sigma x, this is sigma y, and this is sigma z. These aren't standard deviations, by the way, so don't accidentally confuse them for being a standard deviation. Alright, so what's next? Alright, so what do these matrices actually represent, and why do we care about them? Now, we care about them because they help us calculate, not really calculate, but they help us simplify things down a ton. So instead of writing these big chunky matrices here, we can instead just replace them with sigma x, sigma y, and sigma z. And if we want to calculate the expectation value for one of these operators, this helps us out a lot because it helps us do a lot of simplifying. These operators can also be used in general to help us find the probability that you measure a particle. It's a probability that on the spin of a particle, the spin state. I'm trying to figure out how to phrase this. Like, if you were to measure Sx, for example, for a particle, it kind of tells you the rules for the probability densities that result from that. And I can't really go much further into that because again, I don't really fully understand how this thing works. I'm kind of making this video to kind of help myself be better at this subject. But gosh, Griffiths has a terrible expression of spin. But yeah, those are the Pauli spin matrices. Now going back to how we found SZ, I'm trying to look at my reference here, and I don't remember if I wrote down how you would find SZ. Just give me one moment. Let's see if I can try to find it. Wait a second. Wait a minute. No, never mind. I think I just forgot. should write this down. But yeah, those are the Pauli's spin matrices, and that is the algebraic theory of spin. I hope you guys enjoyed this video. And yeah, that's pretty much it. Have an amazing day. Bye.